Welcome back. In this video, I'm going to walk you through a few examples of the first method of running a two-sample t-test, which is called the critical value method. In the critical value method, you calculate a t-score using a formula, and then you look up the critical value in a table, and then you compare the t-score to the critical value, and then you make a decision. So here's our first example. So the question that we're interested in is, do working college students tend to be sleep deprived? In other words, is the mean is the mean hours of sleep of the working student population lower than the mean hours of sleep of the non-working student population? That's the question that we're hoping to answer. And we're imagining that we do a survey, or that someone does a survey, and in the survey, 50 people are randomly selected from the working student population, and 50 people are randomly selected from the non-working student population, which is a total of 100 randomly selected people. And the hours, well, each of these 50 people is asked, how many hours of sleep do you get per night? And each of these 50 people is also asked, how many hours of sleep do you get per night? So both samples are surveyed, and these are the data, or these are the statistics from the data. So this says x equals 6.2. This is the mean of the 50 selected working students. It should say x bar, but I forgot to put the bar right there. And S is standard deviation. So this is the standard deviation of the 50 working students. Over here, we have the sample mean for the 50 non-working students. Their average is 7.4 hours, and their standard deviation is 1.5. So overall, we have the mean and standard deviation of sample 1 and the mean and standard deviation of sample 2. We're going to be using this to calculate the t-score. And let me just talk a little bit about why the t-score is needed. So even though we have the mean of this sample of 50 people and the mean of this sample of 50 people, we don't know what the population means equal. In other words, we don't know what the mean of all working students in this population equals, and we don't know what the mean of all non-working students equals. So the mean of this population is still a question mark, and the mean of this population is still a question mark, because this mean of 6.2 is just an estimate of the population mean for working, and this 7.4 is just an estimate of the mean for non-working. So that the two population means could be equal or they could be different. We're not sure. And there's two possibilities. The first possibility is that the two population means are equal, and the two populations are equal in sleep on average. The other possibility is that the two populations are different on average, and the two population means are not equal. And one or the other has to be true. Either the population means are equal, or the population means are not equal. And those two possibilities are actually our null hypothesis and our alternative hypothesis. So let's set those up right now. So remember, in a two-sample t-test, the null hypothesis is the possibility that the population means are equal, and the alternative is the possibility that the population means are not equal. That's always the case in a two-sample t-test. I described that in the earlier video on the two-sample t-test. So we just have to make that statement, but we have to make that statement in the context of our example. So here, H0 is, well, remember H0 is null hypothesis, H1 is alternative. So we're going to write those out right now. H0 is the mean hours slept per night by working students is equal to the mean hours slept per night by non-working college students. The population means are equal, basically. And H1 is the same exact statement, except instead of equal, it's not equal. So H1, the alternative hypothesis, is the possibility that the population means are not equal. They're not the same number. So remember H0, null hypothesis, H1, alternative hypothesis. In a two-sample t-test, H0, the null, says that the population means are equal. H1, the alternative, says that the population means are not equal. Now we have to calculate our t-score. In the video on Introduction to Hypothesis Testing, I mentioned that in a hypothesis test, you calculate a test statistic that leads you to a decision about whether to reject or retain the null hypothesis. And I mentioned that if the test statistic reaches a cutoff point called the critical value, then you're confident enough to reject the null hypothesis and say that that there is something out there, basically. So in this case, we're going to in the two-sample t-test, the test statistic is the t-score. And in what you do is you calculate the t-score, then you go to the t-table to look up the critical t-score, and then you compare the t-score to the critical value. And if the t-score that you calculate reaches the critical value, you reject the null hypothesis and you say that I'm confident that the population means are not equal. I'm confident that the null hypothesis is false and that there is a difference between the population means. If the t-score doesn't reach the critical value, you retain the null hypothesis, which means you say that you're not confident enough to say that there's a difference between the population means, and you're going to give the null hypothesis the benefit of the doubt. So let's calculate our t-score. So first I need to go over this t-score formula. So it's made up of three different symbols. So x bar is sample mean, s is sample standard deviation, and n is sample size. So what we have is in here is the mean, standard deviation, and sample size of sample 1, which is working, and the mean, standard deviation, and sample size of sample 2, which is non-working. So x bar 1, S1, and N1 are all for sample 1. X bar 2, S2, and N2 are all for sample 2, non-working. So let's plug these in. So x bar 1 is 6.2, the mean of sample 1. S1 is 1.3, that goes right there. And it's actually S squared. Notice that right here. So it's actually going to be 1.3 squared. You might remember that this is called the variance. And here we have 50, which is the number of people in sample 1. And now let's plug in everything for sample 2. The mean right here is 7.4. That goes right there. The standard deviation, 1.5, right there. And the sample size of 50, right there. So now we have all 6 numbers plugged in. And we can solve this using just a few steps. I'm not able to show every step right here, but I might upload a separate file showing the steps one at a time. So what we do is, well, first of all, we start at the bottom in the denominator, and we square our standard deviations. So we do 1.3 squared, and then 1.5 squared. After we do that, we can actually just add those two numbers. Well, actually, we can just add the two fractions because the two fractions have the same denominator. They're both 50. So we can just add the two numbers and put the total over 50. And then we get one fraction with 50 on the bottom. Then we divide the fraction. We divide the total by 50. And after that, we just get one number under this square root. And then we just take that square root, and after that, we just have a number on the bottom of the fraction. Once we get to that point, we subtract on top, and then after that, we're left with just a fraction. one number on the top, one on the bottom. Then we divide the numerator by the denominator, and we get the t-score. So like I said, take the square roots on the bottom. I'm sorry, square the two numbers on the bottom, which is 1.3 squared and 1.5 squared. Then add the two fractions and get the total. Then divide the fraction and just get one number under the square root. Then take the square root and you'll get just a number on the bottom of the fraction, on the bottom of the t-score. Then subtract on top, and then just after that you'll have a fraction, and then divide the top by the bottom and you'll get the t-score. And our t-score comes out to negative 4.29. Now what we need to do in part C is look up our critical value. So what we do is we go to the table I showed you last time. Well, it's actually the table that we used in the third confidence interval situation, which is this table is called the t-table. And actually I have the t-table posted under pages. So you have to go to the t-table to look up the critical value. And in the t-table, there's a column at the left that says df. So df is just n minus 1. It's one less than the sample size. And the df is actually the name for the n minus 1 that we've been using all semester, or almost all semester, for the sample standard deviation. Whenever we divide by n minus 1, we're dividing by something called df. So let's get that right now. So we have the sample sizes are both 50. They're 50 and 50. So we subtract 50 by 1 and get 49. If the two samples sizes had been different, what we would do is take the smaller one and subtract that by 1. But if they're equal, we just take that sample size and subtract by 1. So it's 49. That's the row of our t-table. So we go to 49, well, row 49 in the t-table. Then the confidence levels are at the bottom. And just like when you create a confidence interval, in a two-sample t-test, the confidence level is typically set to 95%. That's what's commonly used by default. So we're just going to follow that and use 95% in our class. So we'll go to 95% on the bottom and go to 1.68. Well, I'm sorry, well, in my problem it's 1.68, but go to where 95% and your df meet up, and you'll get your critical value. And in my problem, the critical value was 1.68. Now what we need to do is take that critical value and mark it on a number line in part D. Actually, the critical value and its opposite. So we got, from the table, we got 1.68. So we need to mark off 1.68 and negative 1.68. And now this divides the number line into 3 areas. And we have to find out which area contains our t-score, because each of these 3 areas leads to its own conclusion in a two-sample t-test. So if the t-score is in the left area, which is called the negative rejection region, you conclude that the mean of population 1 is lower than the mean of population 2 confidently. If the t-score is in this right area, which is the positive rejection region, you conclude that the mean of population 1 is higher than the mean of population 2 confidently. And if the t-score is between the two critical values, which is the area called the non-rejection region, you just say that you're not confident enough to say that there's a difference between the two population means. So you're either going to confidently conclude that the mean of population 1 is lower, the mean of population 1 is higher, or say that you're not confident that there's any difference between the population means, depending on which area the t-score is in. So here we have the t-score is in the negative rejection region, at the left end. So we're going to confidently conclude that the mean of population 1 is lower than the mean of population 2. And this left area, this negative rejection region, starts at the negative critical value. So if the t-score was exactly negative 1.68, that would count as being in the left area. Also, if the t-score was exactly 1.68, that would count as being in this right area. So these two, the left area and the right area are called the rejection regions. I said that they're the negative rejection region and the positive rejection region, and I said that the middle is called the non-rejection region. So if your t-score is in the left at the left end or the right end, you reject the null hypothesis. So if the t-score reaches this critical value or further out this way, reject the null hypothesis. If it reaches this critical value or further out this way, reject the null hypothesis because it's in one of the rejection regions. If the t-score is in the non-rejection region, which is in between, you make the other decision, which is called retaining the null hypothesis. And if you think about it, this should make sense because if the t-score is out here and you're concluding that the mean of population 1 is lower than the mean of population 2, you're concluding that there is a difference, and you're rejecting the possibility of no difference. So that's rejecting the null hypothesis. If your t-score ends up out here at the right end, you're confidently concluding that the mean of population 1 is higher than the mean of population 2, and you're confidently rejecting the possibility, the null hypothesis, that there's no difference. And if your t-score is in between, then you're just you're not concluding that you're not confident that there's a difference. So that's retaining the null hypothesis. So here, our t-score is in the rejection region. So you reject the null hypothesis. And our conclusion is the mean hours of sleep of working students is lower than the mean hours of sleep of non-working college students. That's what we're confidently concluding. Now let's go through a second example. So we have the same research question, but we have a different data set. The mean and standard deviations are different. So our null and alternative are the same because the situation hasn't changed. So H0 is still saying that the mean hours slept per night by working college students is equal to the mean hours slept per night by non-working college students. And H1 is the same statement except saying not equal. And now let's calculate our t-score using the same steps. So now we have a t-score of 0.36. And now we just go to our t-table and we look up our critical value. It's still 1.68 because our sample sizes haven't changed. So now let's mark off our critical value and its opposite again, and mark the t-score. And now the t-score is in between the two critical values. in the non-rejection region. So this means we're not going to reject the null hypothesis, we're going to retain it. That's the answer to part D. And since we're retaining the null hypothesis, our conclusion is that there isn't enough evidence to conclude there's a difference between the mean of population 1 and the mean of population 2. In other words, in our situation, there isn't enough evidence to confidently conclude that there's a difference between the mean sleep time of working and the mean sleep time of non-working college students. And now we're finished. So if you end up rejecting the null hypothesis, your final conclusion will depend on which rejection region your t-score is in. If your t-score is in the negative rejection region, you're going to say that you're confident the mean of population 1 is lower than the mean of population 2. And if it's in the positive rejection region at the right end, you're going to confidently say that the mean of population 1 is higher than the mean of population 2. But if you reject, your conclusion will go one way or the other. But if you retain the null hypothesis, this will always be the conclusion. And yeah, so these are the two examples I wanted to share for the two-sample t-test using the critical value method, which is the first way of doing the two-sample t-test.